All right, let's get right into it. Today, we're doing a super focused prep session on a topic you are almost guaranteed to see on any technical exam: graph and network structures. We're going to break down exactly what you need to know to absolutely crush those questions.
So, are you ready? Let's dive in. Forget about those dry, dense textbooks. We're going to tackle the exact kinds of questions your professor is likely to ask, breaking them down one by one. By the end of this, you're going to feel more than ready. Okay, first things first, we have to nail down the absolute basics. You will, I guarantee it, see a question on this. So let's make sure we've got it locked in tight. So, what is a graph? At its heart, it's actually super simple. It's just a bunch of points, which we call nodes or vertices, and the lines that connect them, which we call edges. That's it. Think about a social network, a city map, or really any system that's all about connections. Now, that leads to the classic follow-up question that every instructor loves to ask. How do you actually take this idea and store it on a computer? Because this isn't just theory, right? We need a way to code it. There are two main ways to do this, and you absolutely positively have to know the difference. And here they are. This slide gets to the heart of a massive trade-off. On one side, you have the adjacency matrix. Think of it like a big spreadsheet. It's incredibly fast if you want to check, hey, are node A and node B connected? But wow, it can be a real memory hog. That O of n squared complexity means its memory use can just explode, especially for sparse graphs where there aren't many connections. On the other hand, the adjacency list is way more memory-friendly since it only stores the connections that actually exist. This is a classic exam scenario, choosing between speed and space. Okay, so we figured out how to store our graph. What's next? Well, the next big question is always, how do we explore it? How do you get from point A to point B? For that, there are two famous strategies you need to know: DFS and BFS. Let's start with strategy number 1, Depth First Search, or DFS. The name really tells you everything you need to know. This one is all about going deep. It picks one path and follows it as far as it can possibly go before it ever even thinks about backtracking. It's a real explorer. And here's the logic. Imagine you're in a maze, and you decide to solve it by always keeping your right hand on the wall. You follow that path relentlessly until you hit a dead end. Only then do you turn around, go back to your last choice, and try a different turn. That's DFS in a nutshell. But wait, how does it remember where it came from? Well, its secret weapon is a data structure called a stack. Every time it moves to a new node, it pushes its old location onto the stack. When it hits that dead end, it just pops the last location off the top and boom, it knows exactly where to backtrack to. That last in, first out behavior is the engine that powers DFS. Now for our second strategy, Breadth First Search, or BFS. And if DFS is the deep-diving explorer, BFS is its cautious, systematic cousin. Instead of diving deep, this one explores layer by layer, kind of like ripples spreading out from a rock thrown in a pond. And you can see how different the logic is. BFS starts at a node, and then it visits all of its immediate neighbors first. Once it's done that, and only then does it move on to visit their neighbors, and so on. It's a much wider, more methodical search. So how does it pull this off? Its secret weapon is the queue. As it finds neighbors, it adds them to the back of a line. And it always processes the node at the very front of the line. This first in, first out system is what guarantees it explores level 1 completely before anyone from level 2 even gets a look in. So this all leads to probably the single most important exam question you're going to face. Which one should you use and when? The answer really depends entirely on the problem you're trying to solve. So let's break it down. Okay, this table right here, this is your golden ticket. Seriously, pause, take a screenshot, whatever you need to do. Notice they have the same time complexity. That's a classic trick question. But the differences are huge. DFS goes deep with a stack, BFS goes wide with a queue. But the most critical difference, the one you really need to remember, is in that last row. BFS is guaranteed to find the shortest path in an unweighted graph. DFS makes no such promise. So let's make this really simple. When should you think DFS? If the question is just asking, hey, does a path even exist between these 2 points? DFS is great for that. Or if you need to find cycles, or if you're solving a puzzle like a maze where you have to explore every single nook and cranny, DFS is your go-to. On the other hand, if the question uses the magic words shortest path, especially in a graph where every connection has the same cost, your brain should immediately light up and scream BFS. Think about finding your friends of friends on a social network. That's a level-by-level problem, and it's a perfect job for BFS.
Okay, so this is all great for an exam, but does any of this stuff actually matter in the real world?
Oh,
Absolutely. These algorithms aren't just stuck in textbooks, they're running all around you every single day.
I mean, just think about it. When you use Google Maps to find the quickest route, you're using a souped-up version of BFS. When a social network suggests a friend you might know, yep, that's graph traversal. These concepts are literally the foundation of so much modern technology.
All right, if your brain is feeling full and you can only remember one thing from this whole session, make it this. This is your ultimate cheat sheet. For storing the graph, matrix if it's dense, packed with connections, list if it's sparse. For searching the graph, DFS to go deep, BFS for the shortest path. Honestly, that one sentence will get you through about 80% of the questions you'll face.
And there you have it. You're not just memorizing abstract theory for a test. You're actually understanding the fundamental logic that powers so much of the digital world around us. So the next time you ask for directions, you'll know exactly what's going on behind the scenes. You've got this. Good luck.